Hello, welcome. Thanks for watching. We're doing lesson 3.5. We're still looking at dilations and scale factors. As a reminder, what is dilation? Dilation is this thing that either blows up an image or shrinks an image. It either enlarges an image or shrinks an image. And the scale factor is this number that we multiply by. And when we multiply by numbers bigger than 1, 2, 3, 4, 5, the numbers get bigger. So therefore our shape is enlarging. And when we multiply by numbers less than 1, such as a half or a third or a fourth, well then you're shrinking down to something because you're getting smaller. So we're going to look at dilation and look at some more of the nitty-gritty details about our shapes. Okay, that's kind of what we're looking at today. So let's take a look at this first example here. Investigate the lengths and slope relationships with dilation. So we have this figure right here from A to B. Let's figure out how long AB is. Distance formula, if you recall, is right here. Run squared plus rise squared. It's using the Pythagorean theorem. Okay? This side is length 1. This side is length 2. So some people think of it as run and rise. I've been saying A squared plus B squared. It's all the same, right? It's the sides of a triangle. So let's do that math super quick. The square root of 2 squared plus 1 squared, that's the square root of 4 plus 1, which equals the square root of 5. So the length of AB is root 5. What is the slope of AB? Well, slope is rise over run. So to go from A to B, right, we're going down 2 over 1. So our rise is negative 2, and our run is positive 1. So our slope is negative 2. That's a bit of a throwback to Algebra 1, rise over run, right? So that's our original image. Now we're going to dilate this thing. We're going to dilate this and see what happens to our shape. So we're dilating from the origin by a factor of 3. So do this with me here. How far away is A? It's up 2 over 1. We're going to triple that. So instead of going up 2 times 3 is 6. And instead of going over 1 times 3 is 3. So up 1, 2, 3, 4, 5, 6, and over 1, 2, 3. There is A prime. And we're going to use the same strategy to B. This is a review from our last dilation lesson. B is 2 away. 2 times 3 is 6. 1, 2, 3, 4, 5. It goes off the page just a wee bit, but that's okay. There's B prime. And here is our image. So let's compare and contrast our pre-image and image. Let's see what the differences are or the similarities. So let's calculate the length of A prime B prime. Well, the length of A prime B prime, it has a run of 3 and a rise of 1, 2, 3, 4, 5, 6. So now the triangle is 6 by 3. So when we do our calculation, 6 squared plus 3 squared equals the square root of 36 plus 9, which is the square root of 45. Now, what should be true? What should be true? If the dilation is a factor of 3, this should have tripled to become this. So is the square root of 5 3 times the square root of root 5, right? Can I triple this and get this? The answer is yes. How can we prove that here? Well, you guys might remember from Algebra 1 how to simplify square roots. Ms. Danana or Mr. Derek might have taught you to find the biggest perfect square inside of root 45, which would be 9. It's 9 times 5. We can take the square root of 9. That's a 3. But I can't take the square root of 5. So I leave it under the radical. So this and this are the same thing. Square root of 5 and 3 root 45. So we have just shown that our image is 3 times the length of our pre-image, which makes 100% sense because our scale factor was 3. Now, does the slope change? That's something kind of interesting to look at. Well, how are we getting from A prime to B prime? We're going down 6 to the right 3. So what is the result of that? Down 6 is negative 6 over 3. Rise over run. Well, negative 6 divided by 3 just reduces down to negative 2. So what have we noticed? What is the length relationship versus what is the slope relationship? Well, our image is equal to the scale factor times the pre-image. That's what happened, right? We took our pre-image, which was root 5, and if you were to multiply it by 3, which is the scale factor, well, then you get our image, which we found to be 3 root 5. That's what I'm saying in words here. I didn't use numbers, I used words. Our image is equal to 3 times the pre-image, the scale factor. But what was true about the slopes? Slopes stayed the same. And that's something that's a pretty big deal about dilations, and you've probably already kind of picked up on that. Clearly, distances are changing when we shrink or enlarge. That's pretty obvious that distance is going to change, that the length of the side is going to change. But hopefully something that you already noticed from our dilations is that the shapes overall were the same, right? A triangle still looked like the same triangle, just a little bit bigger or a little bit smaller. That's because the slopes are staying the same. The length is changing, but the proportions are staying the same, right? Let's look at angles here. So what is the measure of DEA? Use a protractor and measure all 3 angles. Well, we don't have a protractor to use right now, but spoiler alert, this is a right angle, so that's 90 degrees. And these 2 angles are 45 degrees. Now, let's take this shape, triangle DEA, and dilate it. And in this case, we're going to dilate it and make it bigger because the scale factor is 2. Let's double all these distances. So our center of dilation is at the origin once more. And when we double all of these distances, how far away is E? It's up 1 over 1. So double that, up 2 over 2. There's E prime. Up 1, 2, 3, 4 over 1 to get to D. So double that, up 5, 6, 7, 8, and over 2. There's D prime. D, not B, my bad. And A is over 1, 2, and up 1. Double that over 1, 2, 3, 4, and up 1, 2. There's A prime. So there's our image. There's triangle D prime, E prime, A prime. Well, if the slopes are staying the same, that means that the intersections are identical, right? If the slope of this line is the same as the slope of this line, and this side has the same slope as this side, we're essentially creating the exact same intersection. I hope I'm not blowing anyone's mind with that, right? It's something that we see and we kind of have this intuitive sense, but it's honestly something that's pretty important, that when you dilate, all of these angles are going to be the same as they were. 90, 45, and 45. Angles are equal. They stay the same when we dilate. That's a pretty big deal that they're going to stay the same. They are equal. So how did knowing the dilations of segments from equal slope help us support what we concluded in D? That's kind of what we already said. Equal slopes creates equal angles. So, in a nutshell here on this page, what should we know? Dilations change distance, they change size, but they don't change the shape. They don't change the overall integrity of the object. If you've got a triangle, you're going to have that quote unquote same triangle in the end. Not quite the same though, right? Not quite the same. It's either going to be bigger or smaller. So here's the list of properties for dilation, something that we've had already previously mentioned, but we're mentioning it again here. Angle measures stay the same. Basic, I mean, I don't want to overwhelm you with these buzzwords, betweenness, collinearity, right? Just realize that the only thing that's changing is the size. The shape and all that jazz is staying the same. All right, that's what all of this is saying in a nutshell. I don't want to overwhelm you with vocab there. Feel free to take the time to read those, but I just want you to get the gist. Size changes, the shapes does not. So, are we missing an image here? Looks like we're missing an image here. That's my bad. Let me go ahead and draw in the image, and you can draw in the image with me as well. I thought I added these back in. That's my mistake. So here's that four-sided shape, and here's this slightly larger but similar looking four-sided shape. Okay? So we know that this is 2 and this is 3. We know that this is 4 and this is 6. Okay? That's what we know. What is the scale factor of ABCD to EFGH? Read that phrasing very carefully. What is the scale factor of going from ABCD to EFGH? In other words, it's shrinking. So our scale factor needs to be less than 1. Something that we learned from the previous lesson was that scale factor can be found by doing the following. Image over pre-image. So if we're going from ABCD to EFGH, the before is your pre and the after is your image. So when we say image over pre-image, take a distance from this shape, let's say 3, that's the image over, take a distance from the other shape, 6, right? Don't choose 4, right? Because those don't correspond. Don't do that, right? 3 corresponds with 6 and 2 corresponds with 4. So 3 over 6 results in a scale factor of 1/2. And that was probably pretty obvious to most of us. But sometimes when it's not obvious, this is something you can always rely upon. Image over pre-image will result in the correct scale factor. That scale factor is 1/2. So what is the scale factor going the other way around? We'll just flip that, right? Image over pre-image this time is 6 over 3, so I get 2. Oh, something that I didn't write in here that is given to you, that is 30 degrees. I forgot to write that one in. So I gave you two sides and an angle. So we need that to answer question 15. What is the measure of angle H? Well, what did we just realize from above is that angles stay the same. So if this angle is 30, when we shrink this shape down, right, this shape is just going to correspond with this one. So H and D match up. So therefore H is also 30 degrees. FG, well, this is a parallelogram, which maybe you're familiar with, maybe you're not. However, the fact of the matter is that this side is congruent with this side in a parallelogram, and this side is congruent to this side in a parallelogram. You have learned about parallelograms at some point, and we'll talk some more about parallelograms in our class, but that's just a little taste there. FG is 2. So if FG is 2, well then we can make all kinds of conclusions that this is 4 and this is 6, so on and so forth, okay? So what is the perimeter of A, B, C, D? Perimeter means to add up all the sides, go all the way around, okay? So 4 plus 4 plus 6 plus 6 is 20. So I added up all the sides here and got 20. Add up all the sides over here and get 2 plus 3 plus 2 plus 3 is 10. A little question off to the side here. What do you notice about the ratio of the perimeters? Well, 20 over 10 gives me 2, just like the scale factor, or 10 over 20, depending on which way you're going, right? Enlarging or shrinking. But because perimeter is deeply connected with length, right? If the length changes of the sides, well then of course the perimeter is going to change along with it. So if the length of the sides doubled, well then that should mean that the perimeter is going to also double. They're one and the same essentially. 2 to 1 or 1 to 2, whatever you want to call it. All right, so we're really trying to nail it in here, some of the relationships that occur, right? We saw with reflections and translations and rotations that everything stayed the same. It just simply was switching positions. That's not exactly the case with dilations. The angles are staying the same, the slopes are staying the same, but the size is changing. And that's what we're taking note of here, is how the side lengths are changing, but the angles and whatnot are staying the same. So that's really what we're trying to nail here. So with these last two examples, we're gonna just work on finding scale factor, kind of, all right, and using scale factor. So these two things are a dilation of one another. You might not see exactly what takes you from 11 to 5.5, right? How am I going from this number to this number? Or the other way around, how am I going from this number to this number? Right? What is my scale factor? It might not be obvious to you, right? This is where doing image over pre-image really matters, okay? So let's call this the image and this the pre-image. What is the scale factor that takes me from 11 to 5.5? Well, or the other way around, I should say, right? This is my image. So how did I go from 5.5 to 11? This is my before, and this is my after. How do I get from the pre-image to the image? Well, image over pre-image gets me 2. 11 divided by 5.5, plug that into a calculator, you get 2. So some of you might have noticed that 5.5 times 2 gives you 11. If you did, great. But if you didn't realize that, you might be sitting there guessing and checking like, okay, what is it? Like, how do I get from 5.5 to 11? Just plug it in. Image over pre-image, and you get this nice pretty answer of 2. So if the scale factor is 2, let's use that. How do I find x? Well, x and 8, right? I dilate this and make it bigger. 8 times 2 is 16. Okay, well, I have 8, but I'm trying to go backwards and figure out why. Well, if the scale factor to enlarge is 2, then the scale factor to shrink is a half. And half of 8 is 4. With me on that? Let's do it again. So you take a look at the image and the pre-image. So let's call this one the image and this one the pre-image. It honestly does not matter which one you call the image and pre-image here. You're not going to get a wrong answer. Okay, you just need to make sure you stick with that. All right, if that makes sense. So I'm deciding that, you know what, this is my image and this is my pre-image. So to find our scale factor, you do image over pre-image. So 6 divided by 4. I have to, I don't know any other lengths except for 6. So if 6 is my image, I have to choose the corresponding side. I can't do 6 over 8. I understand that that's one of the pre-image lengths, but it's not the one that corresponds with 6, right? Corresponding meaning they match, right? This side and this side go together, right? So image over pre-image, I get a scale factor of 3/2. That is not a typical scale factor that we've seen. We're spicing it up a little bit, right? You could also write that as 1.5. So it's not getting twice as big. It's only getting 1.5 times as big. And that's a perfectly acceptable scale factor. It's okay to get 1.5 times as big. Life isn't made up of whole numbers everywhere you go, right? It's okay to get 1.5 times as big. And I'm willing to bet that that was not obvious for most of us, right? How do I get from 4 to 6? That's why we use this. This is our friend. Image over pre-image. It gets 3.5. Sorry, it gets 3/2 as big. 1.5 times as big. So now let's use it. Let's use that. If getting sorry, let me erase some of this. Or let me clean it up, but I want to rewrite that. If going from this to this, you're multiplying by 3/2 because it's getting 1.5 times as big, that's what we need to do to each of these numbers. Multiply by 3/2 and you get x. Bloop. Multiply by 3/2 and you get y. So what do we end up with there? 6 times 3 is 18, divided by 2 is 9. 8 times 3 is 24, divided by 2 is 12. So this is 9 and this is 12. And that's that. We did it. Please keep that in mind at all times when finding your scale factor. Image over pre-image. Grab a length from the image and grab a length that corresponds with it from the pre-image. Image over pre-image, boom, you have your scale factor. It's as easy as that every time. You don't have to guess. You don't have to look at it and times 2, times 3, right? Image over pre-image, boom, you've got it. All right, and with that being said, there's our last lesson of Unit 3, Transformations. I will see you in class. Thank you for watching. Have a great rest of your day.